All right, so picking up on 2.3 where we left off, we know the shortcut rule, we know the power rule, also the powerful rule is what I like to call it because it's very, very powerful. What we're going to do now is going to enable us to take the derivative of something that's more than one term. If you've noticed, all the things we've taken the derivative of have been a single term. So we have the sum and difference rules and the constant with the k rules. So here's what it says briefly. The derivative of the sum or the difference of two functions is equal to the sum or the difference of the derivative of two functions. So basically, if you have something that has multiple terms, whether it's 2, 3, 4, or 5, whether added or subtracted, and you want to take the derivative of the whole thing, you could just take the derivative of each term separately and then string them together with the correct plus or minus signs. Okay? So terms act really as individual little problems, and you just string them together. Constant multiples can go along for the ride. If you have a constant multiple that's there in the beginning, you can pull them out front and take the derivative of what is left and then take the result and multiply it by the constant. Typically, we don't even separate it, though, because if I had the derivative with respect to x of 3x squared, I'll just use the power rule and call it 6x. But what this theorem tells us we could do is pull the 3 out front and take the derivative of x squared, which is what? 2x, and then multiply by the 3, and you get the same answer. Okay? So constant multiples, they go along for the ride. They're there in the beginning. They're going to be there in the end. You can treat them kind of like as mathematical stowaways or passengers. All right? So here we go. Example 7. Find the derivative of the following functions. We got f of x is equal to x cubed minus 4x plus 5. A handsome little cubic trinomial there. Is every term ready to go for the power rule? Do we need to do any rewriting? No. So we're ready to go. So what's the derivative of the left side? F prime of x. Good. Don't forget the important left side. And now, boom, 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 down the line, x cubed becomes 3x squared minus the derivative of 4x to the first is 4, and then the 5 goes to 0. So you don't even have to write it. Okay? Constants have a slope of 0 everywhere, so their rate of change is 0. The derivative of constant is 0. And linear terms have the same slope everywhere. So negative 4x being a line with a constant slope of negative 4, its derivative is just negative 4. So remember, we're just multiplying and subtracting. Excellent. Let's go one step further. I mentioned already the second derivative. The second derivative we denote as f double prime. Those are not Roman numerals. They're little tick marks. F double prime. To get f double prime, we just take the derivative of the previous derivative. So what's the derivative of 3x squared minus 4? 6x minus 0, or just 6x. And we could do it again. Guess what comes after f double prime? F triple prime, we just add another tick mark. And now what's the derivative of 6x? 6. Now we can do it again. We do not put another tick mark. We don't start counting like you keep scoring dominoes, right? We don't do that. We actually, once we get past 3, we switch to Arabic numbers in parentheses. Okay? So if you see that, f raised to the parenthesis fourth power, it looks like, of x, that means the fourth derivative. The fourth derivative of x is just the derivative of the third derivative, and what's the derivative of 0? Oh, I'm 6, sorry, gave it away.
0.
Dang it. And now what's the fifth derivative? 0. Okay, cool. Once you hit 0, the derivative ever after is 0. Now notice that it started as a cubic polynomial, and we hit 0 for the first time on which derivative? The fourth, right? So if it were a 10th degree polynomial, we should hit 0 on the which derivative? The 11th. Very good. Okay? Now the reason why we put the 4 in parentheses for the fourth derivative is because if I just wrote it like this, f raised to the fourth power of x, that's equivalent to the entire function raised to the fourth power, which is very different than the fourth derivative. So that's why we put it in parentheses. Okay, sweet. Letter B, g of x is equal to that. We have 3 terms. Is every term ready to go? No. But you may be able to take the derivative of the first term without having to rewrite it. And I'm fine. Here's what you do not want to do, though. You don't want to say, okay, g prime of x is, and now I'm going to rewrite the first term, with negative 1/2 x to the fourth, and the other 2 are ready to go, so I'm just going to call that 6x squared minus 5. What's wrong with that? Well, I have the right notation for two of the terms, but the first term I never differentiated. So if you're going to rewrite any one of the terms, you're going to just rewrite all of the terms. And you're going to take the derivative of everything in one line. This is a very careless thing to do, and it'll cost you points every time. So I'll go ahead and take the line, although you probably could do it without. That's negative 1/2 x to the fourth plus 2x cubed minus 5x. And now all three of them are ready to go. Now I'll go to g prime. And I get negative 2, 4 times negative 1/2 is negative 2. X to the 4 minus 1 is 3. Plus 3 times 2 is 6. Subtract 1, you get 2 minus 5. Okay? There you go. You want to keep going till we hit 0? How many more will I have to do? You want to do 4 more? When will a cubic hit 0 on the fourth subsequent derivative? Okay, let's keep going. G double prime of x is now negative 6x squared plus 12x minus 0. Now, G double prime, just kind of looking ahead, G double prime does give you the instantaneous rate of change of G prime. It tells you how the derivative is changing. So if the first derivative tells you how the y values are changing, then the second derivative tells you how the slopes are changing, which is kind of neat. It will have a practical meaning later on, the values of G double prime. When you look to see how the slopes are changing, you're actually talking about the what of the graph? The curvature. Yeah, which that'll come up later. And when we start looking at applications, the original function could be like the position function. The instantaneous rate of change of position is velocity. The instantaneous rate of change of velocity is known as acceleration. So if I go to G triple prime here, G triple prime would be negative 12x plus 12. And the practical application from the Newtonian perspective, what would be the rate of change of acceleration? Anyone know what it's called? It's also a movie with Steve Martin, a funny movie. It's also a guy who would not be welcome into Rachel's Challenge with that attitude. The jerk. It's called the jerk function. Yeah. The rate of change of acceleration is called the jerk, which is easy to imagine. If you imagine a guy at a red light, the light turns green, and he starts accelerating, right? His velocity is increasing, so he's accelerating. What would happen if he had like some kind of problem shifting or transmission problems while he's accelerating? The car would jerk a little bit, okay? So a jerk would be the rate of change of acceleration. All right, let's keep going. What's next after G triple prime? G triple prime probably, I don't know if you saw. He made a cameo in Transformers 2, I think. G triple prime of X. He was a good guy. Yeah. Is it G to the fourth power or G parenthesis 4 or G 4 marks? G4 of X. And we get negative 12. And then finally, the fifth derivative is 0. Okay, I'm sorry. Fewer jokes now, more math. That's why y'all are here. I've never even seen any of the Transformer movies, but I used to watch the cartoons a lot back in 5th grade. They're pretty good. GoBots came out at the same time. GoBots and Transformers were two different companies competing for things that transformed into other things. And the GoBots didn't make it, but Transformers did. Okay, just a little trivia there. Letter C. Oh boy. We got a cubic in the top and a square root of x in the bottom. Is there a rule that says if f of x equals g of x over h of x, then f prime of x is equal to g prime of x over h prime of x? Did we talk about that rule? In other words, can I just take the derivative of the top using the power rule and divide it by the derivative of the bottom using the power rule? No. This is a quotient of two variable functions. And there is a quotient rule for that, but we haven't seen it yet. And when we do see it, it would not be this right here. You can't just take the derivative of the top and the bottom and divide out the results. So that's a no-no. So right now, if the only tool that you have is a hammer, you have to start making everything look like a nail, right? Our only tool is the power rule. So we got to make that look like it's power rule friendly. So guess what we can do? One of our strategies, which we'll be using all year long, split it up. We can put every term in the numerator over the entire denominator. And this, bless you, is the easiest way, bless you, to get this done. Bless you all. I'm not even ordained. 2x cubed over 2x to the 1/2 minus 3x squared over 2x to the 1/2 plus 7x over 2x to the 1/2 plus 5 over 2x to the 1/2. We're like ungetting a common denominator. Okay? Now the benefit is I have what? 4 terms. Are they all ready to go now for power rule? No. Now I have to rewrite y again. I have 2/2, also known as 1, so the coefficients divide out, and I have to come up with an x to a power. So remember, the rule says when you're dividing, you subtract the exponents. So 3 minus 1/2 is 1/2. Well, it's greater than or equal to 1/2. Okay? And less than or equal to 5/2. 3 is how many halves? Have 3 pizzas, cut them into 2 pieces apiece. You eat all 3 pizzas, you pig. How many pieces halves have you eaten? 6, okay? So 6 halves minus 1/2 is 5 halves. We got to be good with working with fractions because with the power rule, that's what we're working with a lot of the times. Fractional exponents. Minus, we're going to use 3 halves as the coefficient of the next term. X to the 2 minus 1/2 is still not 1/2. It's 3 halves. Okay, Garel, your big moment's coming. I have 7 halves times x to the 1 minus 1/2. Garel! 1/2. Very good. You just got excited and gave me the third term's exponent in the first term. And then the next one, what do? I don't have an x in the top to subtract with the bottom. Just slide it to the top and call it negative 1/2. Or really, you could say it's x to the 0 if you want, right? Because x to the 0 is 1 and 0 minus 1/2 is negative 1/2. Now, are all 4 terms ready to go? Yeah. And so now for the first time, I'll take the derivative of both sides. dy dx, of course, is Leibniz notation. You can also use y prime. Multiply and subtract. Multiply and subtract, multiply, subtract, multiply, subtract. So we get 5 halves times 1, which is 5 halves, x to the, and here we get to do it again. 5 halves minus 1 is 3 halves. Fun with fractions. 3 halves times 3 halves, 9/4. You multiply straight across. X to the 3 halves minus 1, Garel? 1/2. Fantastic. Plus, 1/2 times 7 halves is 7/4. X to the 1/2 minus 1, negative 1/2. And then finally, the last one, minus 5/4 x to the negative 1/2 minus 1, negative 3 halves. Yeah. Sweet. Now, technically, we're done with the derivative, right? That one line was the only calculus in this entire problem. Before that, it was just algebra, algebra, algebra. And if we want to clean it up now, it's just algebra, algebra, algebra. So the calculus doesn't last that long. It's like magnesium when you light it on fire. It burns brightly and then it's gone. What? I was about to get there. Yeah, I could tell you wanted to do that. There are a couple ways to fix this, okay? The first way to fix this, to make it more user-friendly, would be just to go back through and get rid of all of your fractional exponents and negative exponents. So like if you needed to evaluate that at a certain value, you probably still do not think in terms of rational exponents, right? But you do understand division and square roots, cube roots. So we could call this 5 halves times the square root of x cubed minus 9/4 times the square root of x. And then it becomes plus 7/4 square root of x minus 5/4 square root of x cubed. So that's one version of it, right? If I told you to plug in like a 1 or an 8 or something right now, you could probably handle evaluating that. But later on, when we have our derivatives, we're going to want to set them equal to 0. Because what type of lines have slopes to 0? Horizontal. That's going to be a powerful tool later on. And of course, if we set something equal to 0, we're going to want to F it, right? Which is what? I was trying to make her go, woo! She did. She was on a business call here. What does F it mean in this class? Forget about it and walk away? Factor it. Okay. So I'm going to show you how to factor this. So let's do this. I'm going to take this line, which is technically correct, and I'm just going to scooch him down here. We're going to factor this out. And the first rule of factoring is to look for a common factor. Okay? You can only pull out what's common, meaning the smallest part in any term dictates what you pull out, right? So let's look at the fractional numbers first. We have nothing common in the numerator, right? 5975. But we do have 2's and 4's in the denominators, which is really having a 1/2 and a 1/4. Which one's smaller, a half or a fourth? A fourth. So we can factor out the smaller of the two factors, 1/4. And then we could factor out some pieces of some x's. We have 1½ x's, a half an x, negative a half, and negative 3/2. Which of those exponents is the smallest? Not magnitude-wise, just the actual smallest. Negative 3/2, right. Any negative number is smaller than a positive number. So I'm going to factor out x to the negative 3/2. And now this is serious business, so I'm going to go with the beefy brown bracket. The beefiest of all brackets. Okay? When you factor something out, you are effectively dividing it out. Yes? So here we go. What are we left with? What is 5/2 divided by 1/4? 10. Can you do that in your head? I hope so. If not, you go off to the side and you go 5/2 divided by what I factored out 1/4. Stay. Change. Flip. Good boy. 2. 10. Okay. It's a little bit of work. That was a weird bark. What dog was that? Now, what are we left with x-wise? Think of this ruler in between here as being a division bar. You can't see that on the video, but think of that brown line as being a ruler that's acting as a division bar. When you're dividing out, you subtract the exponents. So what is 3/2 minus, pause, negative 3/2? 6/2, also known as 3. So we're left with x cubed. When you factor out, you subtract exponents. It's the exponent you started with minus the exponent you factored out. Now you can very quickly check. If you were to mentally redistribute back in, what's 1/4 times 10? 10/4, also known as 5/2. Negative 3/2 plus 3. Anyone but Gorell? 3/2. Very good. Okay. It was his day yesterday. Today's your day. Okay. So let's keep going. When you factor a 1/4 out of a 9/4, that one's a little bit easier. Left with what? Negative 9. And now for the exponent on the x. What is 1/2 minus negative 3/2? 4/2 or 2. Sweet. Then you factor a 1/4 out of a 7/4, you're just left with plus 7. What is negative 1/2 minus negative 3/2? That's the same as 3/2 minus 1/2, which is 2/2, or 1. And now on the last one, I'm factoring out a 1/4 from a negative 5/4, so I'm left with minus 5. And now what is negative 3/2 minus negative 3/2? 0. You take out the entire x. So notice how nicely this one turned out. You're left with a pretty handsome-looking cubic in the numerator, and your final answer then, if you wanted to write it, as 10x cubed minus 9x squared plus 7x minus 5 all over 4 square root of x cubed. That's the quickest, fastest, most fun way to put it back into essentially the original format. Factoring out least powers. You probably haven't factored out with funky exponents very often, but we can do it in here. Factoring out is dividing out. And F it in this class means factor it. Okay? Yeah. Everyone good on that? Kind of fun. Kind of fun. Which one would I prefer, or which one would I probably put as an answer choice on the test? Either one of them. Either one of them. I usually kind of put the answer choice that requires less typing on my part. Okay? Which kind of is the beefy brown one. But I have been known to kind of put in a couple of extra seconds on each problem and type more things. Okay? All right, letter D. We're trying to find the derivative of this. It doesn't look like a nail, but I've got the hammer. Is it hammer time yet? Nope. There you go. There will be a way to take the derivative of this later on as it sits, but right now this is a product of two variable functions, and we haven't learned a product rule yet. You can't just take the derivative of the first times the second. You could also do a chain rule if you wanted to leave the exponent there, or if you wrote it as 3x plus 2 times 3x plus 2, you can call it a triple product. We don't have the tools for that yet, okay? So we need to expand it out. So can we distribute the x first? No. Some pre-calc kids think you can. They're so cute in their naivete. You have to make your Aunt Sally proud. Exponent before multiplication. So remember how we square a binomial quickly? Square, multiply, double square. Very good. Square the first. 3x quantity squared is 3x squared, right? 9x squared. Very good. Hasty make wasty. Don't do that. 3x quantity squared is 9x squared. Multiply, you get 6x, and double it, you get 12x. I was making y'all's test questions last night right before Tyler walked in, at which point I showed him the test. No, I hid it. And one, I remember right before he came and bothered me, or asked for help, sorry. Yeah, just kidding. I gave him $20 to leave. I did, didn't I? I did. Yeah, I gave him $20 to leave. I was writing answer questions, and one of the answer questions that I was writing for a wrong answer was someone who squares, multiplies, and squares and forgets to double it. So you'll have a test question where you'll have to do this. Square, multiply, and double, so 6x becomes 12x, and then you square the last, you get 4. I also wrote questions for people who just square the first and who square the last and don't even put the middle term. I also put a test question for someone who squares the first incorrectly and then squares the last with the correct middle term and with a different middle term. So you can imagine all the fun I have making false answer choices. Now I will distribute the x, and I get 9x cubed plus 12x squared plus 4x. Now is it ready to be differentiated? Yes. In Algebra 2, the fun was over, right? Algebra 2 is like expand that and then go to the next problem. Now it's like expand that and let the problem begin. It is now time to BOTC. What does BOTC mean? Bust out the good stuff. Get out the calculus, right? Like when you have friends coming over, your parents are like, these are important people, we're going to use the china. We have china? What's china? It's the stuff we got as a wedding gift that we never use, except when fancy people come over. We're going to bust out the good stuff. It's time to bust out the good stuff, to bust out the calculus. So what's the derivative of the left side? dy dx or y prime? Do I care which one you use? No. Okay. Then we multiply. We get 27x squared plus 24x plus 4. Yeah. There you go. So if this had been to the 22nd power, would we still be able to do it? Eventually, right? You would probably hate me. But if I failed you for not doing it, you would do it because y'all are good students. Or you might just read ahead and figure out what this product and chain rule thing is, which would save a lot of time. Okay? So this would be a very impractical method if the exponent was kind of prohibitive. But for squared or maybe even cubed, it's still within the realms of what we should be able to do. Oh my goodness, another one. They've delivered wow, that's awesome. Yeah, same place. And we'll divvy those up to all the spirit groups. And we owe y'all a debt of gratitude. We're going to have to get y'all some barbecue or something. Y'all have it this period?
Yeah, second and third.
Second and third. Okay, I got to remember that. Second and third period. Thank you, guys. Second and third. All right. Sorry. Here we go. We're done with this one, actually. Here we go. We're done. Here we go. We're done. Yay. Any questions on any of those? Yes. You absolutely could. Yeah. Pascal's triangle is a great way to expand a binomial if it's raised to a kind of a prohibitive power where you don't want to actually just do the sledgehammer method. Yeah. Pascal's triangle, Of course, y'all seen it before. It's 1, 1, 1, and then it's 1, 2, 1. This is for n equals 0. This is for n equals 1. This is for n equals 2. These are the coefficients of your three terms. So let me show you how that would look since you brought it up. Let's say we want to expand 3x plus 2 squared. We're going to go ahead, since it's degree 2, we're going to go to the third line because it starts at 0. We're going to have a 1 as a coefficient, a 2 as a coefficient, and a 1 as a coefficient. And then you take the two terms inside, 3x and 2. So we're going to have a 3x and a 2. We're going to have a 3x factor and a 2. We're going to have a 3x factor and a 2. And what you do then is you take one of them and you start it with the power of 2. So I'll do the 3x to the second power. And then you walk down. So there's to the second power, the first power, and to the 0th power. And then you walk up with the other one, second power, first power, 0th power. And then you just put plus signs in between and you evaluate. And let's see what we get. 3x quantity squared is 9x squared. Times 1 is 9x squared. 2 to the 0 is 1. So there's the first term. Plus 2 times 3x to the first times 2. That's 6x. What's 6 times 2? 12. So we get 12x. Plus over here, anything to the 0 power is 1. So we're left with 2 squared times 1, which is 4. So there's, you can actually see it, square, multiply, and double. There's the 2, and square. So it's probably too big of a tool for something squared, but if you had something to like the 5th power, it goes a lot faster. Oh, you keep bringing ones down this side, and then you add. So that would be a 3, 3. So there's the coefficients for a cubic expansion. And there's also ways to determine it. This is the recursive way to generate Pascal's triangle. Recursive means it requires the line above, but there's also ways to generate the coefficients without doing it recursively using combinations, okay? But that's maybe for another day. But yes, Pascal's triangle. It's also good in statistics. Has anyone here had statistics? You get into binomial distributions, right? It's kind of the same idea. Binomial distributions uses Pascal's triangle. Okay, sweet. What's that? 4 is 1, 4, 6, 4, 1. Yeah. All right, example 8. Find the coordinates x, y, and the equations of any horizontal tangents to the curve y equals x to the 4th minus 2x squared plus 2. All right, so we need to have kind of an overall plan here. I ultimately need to walk away with a couple of coordinates and equations of horizontal lines. But how am I going to get my information? Well, first of all, a horizontal tangent line is going to have a slope of what? 0. And I know that a tangent line is also the same as the derivative at a certain value of x. So here's my plan now. I'll take the derivative of my function. Instead of plugging in values of x, hoping it's going to equal 0 sometime, I'll set it equal to 0 and solve. Okay? So this one's ready to go. So I just go dy dx, or y prime. I'll do both this time. 4x cubed minus 4x plus 0. And now we'll set it equal to 0 because that's the slope of a horizontal line. And now I have a conditional equation. When you set something equal to 0, remember your plan is to F it, which is what? Factor it. And the first rule of factoring is to look for the greatest common factor. In this case, it would be a 4x. Now, we don't really need any kind of fancy tools to factor out nice positive integer values of x, like we did with the fractions. But it works the same way, right? We factor out the 4. 4 divided by 4 is 1. What is x cubed divided by x to the first? Well, what's 3 minus 1? X squared. Good. 2. Minus the 4 divides out, and 1 minus 1 is 0. You're left with 1. Now that factors even more. Keep it equal to 0. That's an important thing. If you have a conditional equation equal to 0, then you got to keep it equal to 0 as you continue to work down. At this point, you could probably rattle off all 3 solutions, which is fine. If not, you need to go one more step. That's fine too. You could factor it, but now you get x equals 0, x equals 1, and x equals negative 1. So those are the 3 locations on this quartic where we have horizontal tangents. So what this thing is going to look like, let's see. Is this function even, odd, or neither? Let's just talk about the function a little bit. It's an even function because when you replace both x's with negative x's, you get the exact same thing. So an even function has what type of symmetry? Y-axis symmetry. What's the y-intercept of this function? 2, right? It's the point 0, 2. So here's what we could do very quickly if we want to sketch it. Here's the point 0, 2. We know it has y-axis symmetry. What are both end behaviors? What's the limit as x goes to infinity and negative infinity? Positive infinity, right? So I know it's going to come in from the top. I don't know if it dips below the x-axis or not. I would need to do a little bit more analysis for that. But I do know it looks kind of like a W. And so it would stand to reason then that I would have 1, 2, 3 horizontal tangents. And I do. And I know exactly where they occur. They occur at 0, -1, and +1. So based upon that information alone, we can already get a decent graph. And if I really wanted to, I could get the y values at 1 and -1 to see if those y values are actually above or below. In fact, I think we need to do that because it says to get the coordinates and the equations of the line. So let's go ahead and find the coordinates. The points are going to be 0, comma something, 1, comma something, and -1, comma something. So when I plug in a 0, I get 2. I already knew that. When I plug in a 1, what do we get? I get 1. When I plug in a -1, because it's an even function, I also get 1. So let me go ahead and lower my expectations, my x-axis right there. And now that's kind of what the graph looks like. It doesn't have any real solutions. So those are the points where we have horizontal tangents. Now we need to write the equations of these actual horizontal line segments. What's the equation of a horizontal line look like? It's just y equals, right? So it's going to be the y values through which the line passes. So the equation of the horizontal tangents, I'll put the equations down here. This one's y equals 2. This one's y equals 1. And this one's also y equals 1. Pretty powerful stuff, setting derivatives equal to 0. They give you the critical points on the graph. Critical in the sense that if I know where those points are and I kind of know a little bit of information about it, I can get a very nice representation of what the graph looks like with a very minimal amount of effort. Okay? All right, any questions on that one? We're having a whole section later on called optimization where we set derivatives equal to 0. Okay? So here's the next question, and you will have one like this on your test. I wrote it last night, as I mentioned. It's important to remember that at any point of tangency, the function and the tangent line itself at that x value have two things in common. At an x value, the tangent line and the graph that it's tangent to have two things in common. Number one, they share a y value, and number two, they share a slope value. Okay? That's important. Why is it important? Because it helps you answer questions like example 9. Find the value or values. Ooh, look at that mathematical foreshadowing right there. Could be 1, could be 2, could be 3, I don't know. Of k, such that this line is tangent to this graph. Find the values of k so that that line is tangent to that graph. Okay. You'll have a multiple choice question like this. How do we even start? Drawing pictures? What's that? Yeah. The function has the unknown in it. So I'm going to start with what I actually know to be true. I have the equation of a line, and it's not in the form I like, but I can put it in the form I like. If we're trying to extract the slope from a line, and it's expanded out, we'll put it in y equals mx plus b form, right? Because m is the slope. So let's go ahead and do that. Y would equal negative 5x minus 9. So the slope of this line is negative 5. Or in fact, let's just go ahead and say, what is y prime? How about that? Same thing, right? Same question. So I have an expression that gives me the y value of the function, and I have an expression that gives me the slope of that function. Well, I want to know then where that line is tangent to this. So at every point of tangency, a graph and its tangent line share a y value. So here's what I could do. I could set the y values equal to each other. So that means that negative 5x minus 9, which is the y value of the tangent line, is equal to, this one's already solved for y, right? That's what f of x is. That equals 2x squared plus kx minus 1. So I set the functions equal to each other. Now, can I solve that and find a unique solution? Why not? I have two unknowns, x and k. So for two unknowns, you need two pieces of information. You need another equation. Gosh, well, what else is equal besides y values at a point of tangency? The slopes. Good. So let's go ahead and find f prime of x. F prime of x by the power rule is 4x plus k. And I already found y prime to be negative 5. So if I come over here and I set the slopes equal to each other, I know that 4x plus k has to equal what? Negative 5. Well, there's my second piece of information. So now I just have to solve these equations simultaneously, and that does not mean one with one hand and one with the other. That means I solve them by either using substitution, guess and check, Kramer's rule, linear combinations. What's probably easiest? I think substitution is probably going to be easiest if I solve this one over here for k. So let's do that. K then would equal negative 4x minus 5. Now I'm going to box that one because it's asking me to find the value of k. So I'll need to come back to that when I'm done. But for now, I'm just using it to create one equation with one unknown. So plugging it into there, I get negative 5x minus 9 equals 2x squared plus kx minus 1. And in the parentheses that I left, I'm putting negative 4x minus 5. Substitution. And now I have one equation with one unknown. So now it's going to work. I just expand it all out. Negative 5x minus 9 equals 2x squared. If I distribute the positive x from both sides, you get negative 4x squared minus 5x minus 1. So I'm going to bring everything over to the right side. So I have a 2x squared minus 4x squared. That's negative 2x squared. And then I have a negative 5x, which when I bring the other negative 5x across, they cancel. And I bring the 9 across, and it becomes positive 9 minus 1 is positive 8. Okay, so now from there, I'm just going to multiply through by a negative 1. Or how about it? I'll just factor out a negative 2. Maybe I'll do that. And I'm left with x squared minus 4, and that equals 0. So now if I factor that, I get x minus 2 times x plus 2. So there you go. I have now two x values, x equals 2 and x equals negative 2. Did I answer the question? No. On the test, you're going to end up with an answer at this point. And guess what answer choices might be there? 2 or negative 2. You've done a lot of work. You're getting to a result. You think that's the answer, but you haven't really answered the question that was originally being asked. You had to find the value of k. So apparently there's two x values where that tangent line is going to be tangent to that graph. How do I find both k values then? Plug them back into here. That's why I boxed it up. So here we go. K is going to equal, if I plug in the 2, negative 8 minus 5, which is negative 13, or k will equal, if you plug in a negative 2, you get positive 8 minus 5, which is 3. So which one's correct? Both of them. Okay, now notice in the quadratic here, the line is fixed. Negative 5x minus 9 is a fixed line. But the coefficient of the x is responsible for moving a parabola left or right, shifting it left or right. I have, I think, the pictures down here of what both looks like. Because it's kind of nice to get a little bit of visual verification. So the tangent line is the same. It's exactly the same on both graphs. But if you notice right here, here's where it's tangent at x equals 2. And here's where it's tangent at -2. Notice the parabola not only shifted left at -2, but it came up a little bit as well. Okay? So one tangent line is tangent to two different parabolas. Kind of neat. All right? Questions so far? You're already kind of seeing some of the cool things that calculus can do. No questions? Oh, nice catch. All right, so in the previous section, you recognized graphically the derivative sign. Remember that? We went to the calculator, and we had the calculator sketch the derivative of, what was it, negative sign, and then cosine and sine, blah, blah, blah. We even, believe it or not, derived it in class at the end of the notes for 1.4, and then you derived the other one in the worksheet for 1.4 when I gave you the composite identity. Okay, we're not going to derive them again, okay, because you can derive these using the limit definition using the composite identities. We're just going to memorize the results now. So I call this the sine and cosine rules, which is a pretty good name for rules that help you remember the derivative of sine and cosine. So here's the first rule. I'll call it the sine rule. The derivative with respect to x of sine of x is, guess what? Cosine of x. That was a good guess. Not a bad guess. Cosine was correct, though. What's the derivative of sine? Cosine. Sweet. And what's the derivative of cosine? Sine would be a good guess. Maybe they're each other's derivatives, but you've already seen. No, it's negative sine. Okay? So the derivative of sine is cosine, and the derivative of cosine is sine. So they're not quite each other's derivatives. But here's something that you can help memorize trig functions as we go throughout the entire year. As we move forward, there's four other trig functions, right? Two of which have co in front of them, cosecant, cotangent. And then there's going to be three inverse co-functions, like arcsine, but I guess with cos, arc cosine, arc cotangent, arc cosecant. Any trig function or inverse trig function that has the word co in it is going to end up being negative, okay? And anything that does not have a co in it, like sine, tangent, secant, arcsine, arctangent, arcsecant, will be positive, okay? Anything that has co will be negative derivative. Anything without co will be a positive derivative. That will help you memorize everything moving forward. It's kind of interesting to see why. Let's do something down here. Let's look at the graph of Sahala. It looks like that. This was 2 pi, this was pi, and this was 0, this was pi halves, and this was 3 pi halves. I'm going to sketch the derivative in blue, okay? You can actually generate the graph of a derivative of a function just like your calculator can without knowing what the equation is. Here's how you're going to do it. You want to graph at the same values of x where you see these y values, you want to graph the slopes of the graph at those respective x values. So the easiest place to start is at your relative maxes and relative mins. Why? What do you know about the value of the derivative at a high point or low point here? 0, okay? So on the same graph, I'm going to sketch the derivative in blue. The derivative of this graph at pi halves is 0. So the derivative is going to have a y value that's going to be 0. Same thing at 3 pi halves. Same thing over here at negative pi halves. Horizontal tangent line means that the derivative is going to be 0. Now all you have to do is look in between. From negative pi halves to pi halves, the function's increasing. See that? It's going uphill. So your slopes are going to be positive. So between the x-intercepts on the derivative, you're going to have values that are above the x-axis. Stop me when the slope is the greatest, most positive slope. It starts at 0 at negative pi halves. As I go to the right, they're getting bigger, 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 bigger. And then right there, I have a maximum slope. And the maximum slope ends up being 1 because after that, my slopes are decreasing back towards 0. So the y values of the graph, which will represent the slopes, start at 0. They increase to a maximum of 1 at 0, and then they decrease back towards 0. So guess what that's going to look like? It's going to look like this and like that. The slopes get bigger, then smaller. And now the same thing happens from pi halves to 3 pi halves. If I analyze the green graph, I started at 0. Now it's like negative a half, negative 2/3, negative 1 is the steepest. and then they start increasing again back towards 0, becoming less negative. That's going to look something like this. And if you keep doing that all the way through, you get the blue graph, which of course you recognize the blue graph as cosine. Yeah. So we'll have a warm-up tomorrow maybe where you get a chance to do that with another graph. So right now we just memorized the derivatives. What's the derivative of sine without me looking? Cosine. Now without you looking, what's the derivative of cosine? Negative sine. Okay. I wasn't looking to see if y'all were looking or not, but I trust y'all. All right. So look at the fun we can have now with our two new rules. We can play with them. If the function is y equals 2 sine of x plus 7, it's a sine wave with an amplitude of 2, and the sinusoidal axis is moved up 7. What's the range of this function, just for kicks and giggles? Negative 2 to 2? Well, no, because we moved it up 7. It's going to go as high as 9 and as low as 5. So the range is 5 to 9, right? Which is, 5 to 9. I think that was a Dolly Parton song. That was 5 to 9, if you played it backwards. Yeah. 9 to 5. Yeah, okay, yeah. With Dabney Coleman. It's a good one. And Jane Fonda. You ever seen it? Okay, maybe after the AP exam. All right, let's take the derivative. What's the derivative of the left side? dy over dx. I like it. It's a shout out to Leibniz every time you do that. Okay, it's a shout out to the little man. What's the derivative of 2 times sine of x? Negative 2 cosine x, positive 2 cosine x, positive 2. So here's where the constant rule comes in handy. I want the derivative of 2 times sine of x. Well, I could just take 2 times the derivative of sine of x, which is cosine. And then what's the derivative of 7? 0. There you go. Very good. Now let's take the second derivative. If you are using Leibniz notation, the second derivative uses Arabic numbers from the beginning. This is the second derivative. This is how we write it. D squared y over dx squared. It looks a little awkward, but here's why it is.
Teachers, please tune in to Channel 4 for the student announcement and also tune in to the NBHS.TV.com. Thank you.
All right, so here's why the notation looks funky. Remember when we have an equation and we take the derivative? I showed you on the very first example, what we're really doing is we're taking the verb ddx of both sides. Okay? So if I take the derivative of the first derivative, I'm taking ddx of dy dx. And if you notice what happens here, it looks like it's d times y, which looks like d squared y. And in the bottom, if you treat dx like an single variable like delta x, dx times dx is kind of like dx squared. So that's why the second derivative in Leibniz notation looks like the 2's are kind of offset from each other. We read that as the second derivative of y with respect to x. And what would that be? Well, what's the derivative of 2 cosine of x? Negative 2 sine of x. Yeah. And the third derivative would be d cubed y over dx cubed. Well, the third derivative would be the derivative of the second derivative, which is what? Negative 2 cosine of x. Very good. So you kind of get the idea. Leibniz notation never has to use the little parentheses around the numbers. It never uses tick marks either. So I kind of like using Leibniz notation. All right, and then the last one for the day, or maybe not. How much time do we have? Bless you. We have 2 more, actually, on this section. What is the derivative of f of x if f of x is x plus cosine of x? Well, what's the left side become? The left side. F prime of x. Yeah, just one f prime of x, though. So you're right. Just one of them. And now we get to combine the power rule with the sine or cosine rule, right? What's the derivative of x? 1. And what's the derivative of cosine? Negative sine of x. Sweet. Okay? Pretty easy if you memorize them. And then letter C. Oh, boy. Can we do this one? This one is a product of 2 variable functions. It's a product of 2 variable functions. And each of those two variable functions have a composite angle inside of them, x halves. And we've only learned the derivative of sine of x, not sine of x halves. So this is going to require eventually what's known as the product rule and the chain rule. We don't know either one of those. Remember, all we've got is a hammer. So we need to make that guy look like a nail. Anyone? Double angle identity. Yeah. Here's the double angle identity. Sine of 2x is equal to 2 sine of x times cosine of x. That's the double angle identity for sine. You do need to know that one. While we're here, the double angle for cosine is cosine squared of x minus sine squared of x. It's the one that looks like Papa Pig, but it's got a minus sign in between. So how is that going to help us? Well, if I can match the form up, I can rewrite g of x. So let's do that. This is really 2 sine of blob cosine of blob. X could be anything. And if I can recognize 2 sine blob times cosine blob, it's equal to sine of twice the blob. So notice I do have 2 sine blob cosine blob. So that's equal to sine of twice the blob. And what's my blob up here? X halves. Well, let me simplify that carefully. What's 2 times x halves? Sine of x. Oh, now it looks like a nail. So g prime is really just the derivative of sine, which is cosine. You got to love a trig proof inside of a calculus question. Fun, 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 fun. Yeah, so 2 sine of x halves times cosine of x halves is really the function sine of x in disguise. And that's a pretty darn good costume, okay? It's not even Halloween yet. But I think there's like Halloween stores open, aren't there? Already, yeah. Okay, we'll go ahead and stop right there for the day. And we did not finish, did we? So it looks like we'll finish tomorrow and the worksheet that we do on the test day. Our test is going to be strictly 2.1 to 2.3. And it's not going to cover 2.2 because that's a calculator section and you won't have a calculator. So it's really over 2 sections. There is a test online. Let me talk about this. There is a test online that I will draw your attention to. If you are interested in trying to practice a little bit early, you may go to the following test. It's the one that I had on my clipboard last night that I was making changes to when Tyler walked in. Okay? And it was this one right here. There's only one that says 2.1 to 2.3. It's from 2015. So that is the one that I modified. Okay? So I literally had that in front of me, and I was going through and kind of just changing the questions a little bit. So if you could do this test, I think that you're going to make 100 on the one on Thursday. You're welcome. Okay? So that's it for today. You got about 2.5 minutes left.